Okay, I would start from where we stopped last lesson. So I just copied the last part of the script. As you probably read, I adjusted some incoherencies that were on the e-learning. One lesson was missing, so one student told me that one lesson was missing, and all the numbers were kind of not synchronized between the videos and the real life, and also the OneNote. So I tried to make everything coherent, and sorry about that. Anyway, so this is what we did as last part of last lesson. Okay. So we loaded the log of the air passengers data, which are already there. We set the last 24 observations to NA, so missing values. Why did we do that? Because, as I told you, the state space form and the Kalman filter work also when data are missing. And so if I just hide or put to NA the last 24 observations, it means I have for free predictions. I don't have to use the predict function to do predictions. So it's just one of the of the alternatives that you have if you want to do predictions or forecasts, actually. So this was the very first part of lesson. Let's just make it run. Then this is probably like kind of the first time you saw this SS model function. It's nice because it lets you use the formula of R, and we could put regressors here, and we will do it later and see how they're managed, but they're automatically managed by the system. Then we have some functions to build the components we're interested in. In this case, we are interested in the so-called local linear trend that we saw a couple of lessons ago. A local linear trend here is a degree 2 trend. That's how it's called in this world. So one would be a random walk, and two would be like a random walk with a slope, and the slope is a random walk. So actually the local linear trend. And the second parameter is the list of the variances, but it could be the list of the covariance matrices, because in this case, we have a scalar y. Okay, this is a scalar time series, but if we have a vector time series, so many time series at once, the trend could be assigned to all time series, and in that case, of course, this would be a covariance matrix of the covariance between the disturbances of each equation. And generally, we assume the disturbances are not correlated across equation, but there are good reasons for giving this possibility. For example, in econometrics, there is a very important situation in which we have common trends. It's called co-integration. I don't know if you ever heard it. So we talked about integrated time series. An integrated time series is not stationary, but it can make stationary by one difference. For example, we say that two time series are co-integrated if you can make a linear combination of the two time series, which is stationary. Okay? That's the situation of co-integration. It's very important, especially in economics, because it means that in the long run, these two time series are like kept together by a very strong force some way, okay? If we have to implement such a model in state space form, this means that we would have like two trends, for example, to local linear trend or whatever, or to random walks, and they have the noise of these two random walks, they have perfect correlation. In that case, it means that they share the same trend in some way, okay? So this is just some few more information I can give you. We don't have time to go also through multivariate models. Maybe I can show you something. Well, in some way we did one multivariate model because the very first example we did with the polar poles, that was a multivariate model, of course, but it was a very simple one. Anyway, this just to tell you that this, why is this a list, not a vector? Because here we can have the covariance matrix of the so-called etas and the covariance matrix of the so-called zetas, okay? And in our case, they're just scalars because we have a scalar time series. Then we have the seasonal component. As I told you, class allows for both seasonal components that we saw, so the dummy and the trigonometric. This is the period, and then again we have the variance. Again, it's just one variance. It doesn't matter if it's a dummy or a trigonometric, we will just have one variance, okay? Because also in the trigonometric version of the seasonality, we assume that all the variances, that are many variances actually, they're all equal, so it's just one variance. Just to make it clear, you know, if we use the trigonometric version of the seasonality, we have a lot of omegas. Okay, they're all white noise. They're all different white noise, but we assume they share the same variance. That's why we only have one variance. Also here, and of course, if you have the stochastic dummy, you just have one noise, and so there's just one variance. But in both cases, we have just one parameter to estimate, which is the common variance in this case of all the omegas. What does it mean? We assume that all the sinusoidal components are evolving at the same pace, at the same speed, okay? So of course we could make a model where we say, okay, maybe the low frequency are evolving, I don't know, slowly, the high frequency are evolving more quickly, but on real application, it really doesn't make any difference given too many variances to estimate. So usually we assume there's just one common variance, and that's, well, actually here we are using the dummy one, so in the dummy version there's just one variance. And then of course there's the h, that again there's a scalar. It's in this case the variance of the observation noise, and again we have to estimate it, so NA is a good choice. So this is always the first step, defining the model, and we define the model, okay? And inside the models, there's really everything. There's the data, there are all the matrices and many information, okay? It's an SS model object, so it's got its own like methods and so on. Anyway, then we have a model, but the model is missing some variances in this case. So we are missing 4 variances. Before we can use the state space form, we have to estimate those 4 variances. And so we have to go through the fit SSM model, which is just a wrapper for the optim function, so the optimization function that usually you use in R. And indeed, you can pass all the options that you want in the optim just as extra parameters here, okay? So the first thing we have to pass is the state space form, okay? So mod 1 is our state space form. Then we have to pass initial values for the unknown parameters. And as I told you more than once, this depends on the so-called update function, which would be the third parameter here, you see. But there is a default that we can use in this case, but starting with the first modification of this example, we will be writing the update function. And the update function, the default update function, assumes that we just want to estimate variances, which are on the diagonal of Q and of H, of course, but they're set to NA, okay, as we did. So The order of the variances that are to estimate, well, it's exactly the order we are seeing here. So first, the so-called eta, then the variance of zeta, then the variance of omega, and finally the variance of epsilon, okay? Because it's the diagonal of Q and then the diagonal of H or the NAs. So if you look at the Q, so this is what we call eta, zeta, and omega. So the free white noise, and then this is just the H. So these are the four variances. They're set to NA, so the update function, the default update function, knows that we want to estimate those. Remember that we have, in order to constrain the variances to be positive or not negative, actually positive, we're constraining to positivity parameters, we are not parameterizing through the variances, but we're parameterizing through the log variances. So when you take the exponential, you get a positive number. And so you're sure that it's a proper variance. And so does the update function use the parameters. So in the parameters, we have log variances. That's why I built initial parameters. They're small numbers because we're moving into the realm of logarithm, which is very small numbers, okay? And of course, we can do some reasoning on how to build initial values that could be this one. They're just initial values, but of course, it's better to give initial values that are at least in the right scale, because first of all, the optimizer will be quicker. And then, and this is more important, the likelihood function of this model is not necessarily concave or convex, whatever you look at, if you want to maximize the likelihood or minimize the minus log likelihood. And that means that it can get stuck into a local optimum, okay? That's why. But usually we have interpretation for these numbers. For example, this first number is the variance of the level, okay? And this is the second is the variance of the evolution of the slope, okay? So usually the slope changes very slowly. So a small number is good. For example, if we fix a number to 0, which we cannot do because we are taking the log, so we can just fix a number which is really close to 0. It means that we are assuming that the slope doesn't change over time. So we're, according to our initial value choice, we're already giving a direction to the model. So a very small second here variance would be a slope that doesn't change. This is how I let the level jump up and down like a random walk. So the larger the jumps. This is the variance of the seasonality. So the third one. The seasonality usually changes very slowly in time. So a small number is also a good choice. And this is the observation noise, which is usually, I would say it's more in the unit of measurement of the real data. So usually this is larger. And I just put these small numbers, but a good way to derive like initial values is to refer to the variance of the data, for example. I remove, of course, the missing. So the whole variance of this time series, because it's a log, is 0.15. That's why I told you small numbers are appropriate. But this in some way gives you the scale of the problem, okay? So you can kind of think of dividing this total variance among the component. Actually, it's not really the component. These are the disturbance of the components, so it's even more indirect. But of course, these variances will be smaller than this variance, okay? So you have like an upper bound for your variances, okay? But hopefully the initial value is not so important. So now we will not define the update function. We can estimate using the update, the default update function. As I told you, inside the fit, so fit, this is like an object, well, probably doesn't have a name, I'm not sure. Yeah, it's just a list. It's got two main slots. The first slot is just the output of the optim function. So if you know the optim function, you know the output of this part. It's called optim out. This is just the set of the parameters at the minimum, because here we minimize the minimum minus the log likelihood, so it's the maximum likelihood estimator. Of course, not of the variances, but of the log of the variances. So you want to check the variances, you have to take the exponential of this. This is the value at minimum, so this is the minus the log likelihood. So change the sign, we get the likelihood. Counts is just the number of times that the function was called, because of course it's a numerical optimization, so the function gets called many times till convergence. And you may have a method that approximate the derivatives, a method that try to avoid approximating the derivative. Actually, usually I use the BFGS, for example. You can always add that. I would say this is the most popular way of estimating like continuous likelihood function in statistics. And this uses like the gradients or the derivatives, but the derivatives they're just approximated by numerical methods, okay? But I mean, we get approximately the same results that we got. And the convergence, as I told you, the convergence parameter tells you if it's there, nothing wrong happened. So convergence was reached. If it's not zero, then you get the message here telling you why the convergence was not so satisfactory. If it's one, it's just because you reached the maximum number of iteration. So you can just increase the number of iteration. I think it works like this. I always have to go by her, but this is just something you pass to the optim function. So if you look at the optim function, you have also the solution. So for example, if I want to put to 1000, I don't know, the maximum number of iteration, I think it works this way. Yeah, it doesn't give any problem. But anyway, these two things here, they're just passed to the optim function, okay? So this is, if you want to see how this like parameter of the optim function works, just look at the help of the optim function, okay? So you can pass any parameter. So you see method is this one here. Actually, it was wrong. It's control, it's not options. For some reason, didn't get any feedback. So control, sorry about that. So you see control, and here there's an explanation on everything you can pass as extra parameters to the control. But anyway, we just go through here, and here, for example, max ID. Okay, but this is, as I showed you, this is just how the optim function works. So we have a satisfactory optimization process here. For example, if we want to just see our variances, because they're just variances, we can just look at the exponentials, or let's do this. Zap small is just a function to cut the too many numbers. So what we see here is actually we get almost this is strange. We get an almost deterministic model, meaning that the local linear trend variance is very small, so it doesn't tend to jump up and down. We just have a slow evolution of the slope, a slow evolution of the seasonality, and then actually no observation error. This is not what I expected, but anyway, usually it's different. But anyway, let's check if we got a coherent model. What should we do? Well, the first thing I usually do here is actually we could check the residual, of course, to see if they're white noise, as we did in the ARIMA world. But then we're also interested in seeing if the components have been meaningfully estimated. So we start with the definition of the model. Sorry, here. So first step. Second step, estimation of the unknown of the models. And then usually third step is carrying out the so-called filtering and smoothing. And here actually we also get the, for example, innovation errors on which we could check if, for example, if they're white noise, or if we are exploiting all the linear information of the past about the future. And so, for example, you can call this KFS1, and we call the so-called KFS, large KFS function. So you can check the help. This is a function that does many things. First, you have to pass a model, a state space form, a complete one. Here you cannot have NA, but now we don't have NA anymore, because in the fit one, I showed you just the optim out, but there's also the model. So this is a state space form, and nothing is missing here, okay? So we will be passing that to the function. So the first thing we're passing is that. Maybe to be explicit, I can just write everything here. So this is not model one, but it's the model of in fit one model. Okay, so we passed a complete model, no missing parameters. Of course, there are missing data, but there are not missing parameters. And then you see we have filtering and smoothing. And that's basically what we're interested in now. All the rest is not interesting for us now. And if you look at into the filtering and smoothing, we have some choice. State filtering is actually what I already described to you. So it's the common filter. So the common filter provides you with, if you remember, like the real-time estimation of the components of the state variables. So using observation up to time t, I'm predicting the components at time t, and also the one step ahead predictors, because the common filter, if you remember, is just like a two-step procedures. There's like the update that goes from one-step prediction to filter, and then there's the prediction step that goes from the filter to one-step ahead prediction. So you get all of these things. You get also the innovation. We saw that the common filter then produces also like the prediction of the real observation and innovation, and also the variance of the innovation, and of course the variance of the forecast error or the prediction error for the components. All of these things are produced. And then we have, well, here it's called signal, it's called mean. We're just using linear Gaussian models, so the signal and the mean will be just the same thing, okay? So in our case, so what's mean or what's the signal? Well, it's just the zeta matrix applied to the estimation of the alpha. That's called the signal. I myself, I think, called it signal quite a few times. So the signal is just like what does the zeta matrix on the alpha vector. Okay, so that's the signal. And then if you go into the smoothing, we have one more choice. We have the state smoothing. We have signal and mean smoothing, which again, once I have the smoothing of the states, of course, I can build the signal just by applying the zeta matrix to the estimates of the alpha vector. But then I also have this disturbance smoother. I haven't described you yet what that is. We will see it later. But it's very useful to find outliers, for example, or structural change in the models, because just an intuition, the disturbance smoother does the same thing that the state smoother does. So the state smoother, if you remember, is just the estimation of the components given the whole time series. And also we can have the estimation of the disturbances of, so the white noise of the component given all the data. And that's what the disturbance smoother does. And as I told you, we will use it for identifying outliers, for identifying like structural change, like abrupt change in the level of the time series, abrupt change, for example, in the slope of the time series. Even we could find abrupt changes in the seasonality of the time series. Sometimes it happens. Just to mention, I'm working with some many actually time series that the Chambers of Commerce of Milan builds, and they, for some reason, I don't understand why. In 2010, suddenly the seasonal patterns changes abruptly. I don't know why. And so you can find it using this disturbance smoother, such changes. So we will spend some time on that later. And that's basically you have to everything you have to know. These are just filtering and smoothing are just strings, or actually vector of strings. So you can pass all the names that you of the object you want. So you could actually let compute everything. And for example, we can write filtering equal, and I say I want the state, I want the signal. The mean would be just the same thing, and that's it. What about the smoothing? I can get, of course, the state smoothing, which is the one we're more interested in. We can also the signal smoothing, and well, the disturbance smoother. We will see it later, maybe. Well, let's just skip it, but later we will ask for that as well. And when we run this, we get a very rich object. I think it's an object of class KFS. So it's really defined as an object class. But of course, object class in R are mostly lists, at least when they use these S3 ways of building objects. So this is our KFS. The KFS again has the model. It looks like the model is just passed to the next function every time. So the model is there, but we're not really interested in that at the moment. I mean, we already have it. Okay, and what is interesting is what it comes after the model. So that starts from here, okay? So ATT, what's ATT? As I told you last time, so the common filter is providing you with, so we called actually AT given T, the projection of alpha T on all the observations from the first one to the Tth one, okay? And that you have here, so it's called PTT. Of course, PTT will be, ATT. ATT will be a matrix, so the ATT in R is a matrix where you have like here the state, so state one. So for example, the level, let's just give it the names we use it. You will have the level, you will have the slope, and so on. You have all the state variables, okay? And of course here you have the filtered level, the filtered slope, and so on. As I told you, this is like the real-time estimation of the components, okay? And so actually it's, I would say, an n times d. I don't know how he calls the dimensions here, but he uses his own numbers here, for example, here. But n, he uses n for the number of states. Okay, so m is the number of observation, m is the number of states. So you have the time in the rows and the state variables in the column. Okay. Of course, this is an estimation. It's a linear projection of what we don't know, which are the state variables or the components, as we call them, on the data. And so it's uncertain. We're estimating something that is really not defined. It's like an abstraction. And so we also have the so-called we call this PT given T, which is like the covariance matrix of the errors I make while predicting alpha using this ATT. Okay. Well, this is the same thing transposed. Okay. So this is the error I make by estimating alpha using ATT, the variance of that error. Okay. So variance and covariances of that error. Of course, the object this is a covariance matrix time series. So the object that contains that, which is called PTT inside R, is just a three-dimensional array, because you have many covariance matrices. Okay, so this is the time, and here you have the covariance matrix. So each of these is PT given T. Okay. So if, for example, if you want to draw confidence bands as around the level, we need just to pick the first top left elements here, and of course through the time, and that's the variance. Then we compute the standard deviation. So we just take the square root, and for example, if we want to be like 95% confidence interval, we can just multiply that. So we take the filter and then make minus or plus 2 times that standard deviation, okay? Or standard error, it's an estimate, so we can call it standard error. We can try to do that later. Okay, then what we have is, so we saw here, ATT, we discussed that now. You see it's, well, it doesn't show here. Well, it's, here you see it. So it is 144 time observation times 13 variables. Why 13? Well, it's easy. We have 2 variables for the local linear trend, so the level and the slope. And then we have 11 variables for the seasonality, so the trigonometric seasonality, so 13. And they also get names. You see it from here: level, slope, Sdmtsa1, Sdmtsa2, and so on. And you see that the PTT is actually a 3-dimensional arrays, and we have the 3rd dimension, which is the time. Okay. You have probably noticed that we have 144 observation and not 120, because as I told you, missing observations are really not an issue. When the observations stop, so the filter actually becomes a prediction, so a forecast for the future, because new observations are missing, but the filter goes on with the information that is still there. And so here we already have like the prediction of the level and the slope and so on of the future. So for the last 24 observation, we have set to NA. M is just the signal, the mean or the signal, whatever you want to call it. So it's zeta times ATT. Anything you have, anyway, you have all, and this is his variance here. You have the description of this, of course, in the help. It's very complete. Okay, this V is very important because it's I think I called it I, but here it's called V. It's the innovations of the models. For example, if you want to do model check and see if you captured all the autocovariance present in the data, you should work with this V. So you, for example, could produce the autocorrelogram of V. Actually, better than using V directly, it would be better to divide V by the square root of F. What's F? Well, F is if you remember here, we use the same letter. F is the variance of the prediction error, the 1 step ahead prediction error. So The innovation is the one step ahead prediction error. So V is one step ahead prediction error, and F is its variance. Why should we divide F by its variance? Well, because the variance at the beginning of the time series is huge. Why is it huge? Because at the beginning of the time series, I'm predicting based on nothing, just based on my initial guess. And my initial guess has variance, infinite variance. Here, we all have the so-called diffuse initial condition. Diffuse initial condition means infinite variance condition. You know, is the case where we say we know nothing about the level at time t equal to 1. We know nothing about the slope, about the seasonality, and so on. So we set the variance, the initial variance, equal to infinite. Of course, my first prediction is an infinite variance prediction. So it would be just a very bad prediction, okay? And then starting by observing the first observations, the variance goes down and down and down, and then it converges to the to a constant. So it's called a steady state variance, okay? And so it would be either better to exclude the initial V's, or if you want to use all the V's, you can just divide the V by the square root of their variance. So, you know, you get like an homogeneous variance time series to check for the autocorrelation, the residual autocorrelation of the model. This is a very important one, alpha hat. As I told you, we use the name AT given N for the smoother. So for the smoother was this object. So it was the prediction or the expectation, if we are in the Gaussian realm, of the state vector at time t, but based on all the observations. So it's not real time, it's ex post in some way. Okay, this is called, and of course we also have the same object for the variance covariance of the errors. In R, this is called actually alpha hat. And this is called, I remember, just V, okay? And this is called V. And of course, they have the same dimension as ATT and PTT. So alpha hat, you see, it's, again, 144 times 13. You know, we have still the states in the columns and the times in the rows. And the V is an array of variance covariances. And mu hat is again this, as I showed, the mean and the signal in this case are just the same thing. So I guess we have it twice, if I'm not wrong. But you can check all the names. I'm not using those very often. That's why I don't remember all the definitions. But anyway, the important things I already highlighted to you. So for example, let's start by seeing, okay, we can check the autocorrelation function of the residuals. So we can take the KFS1 and divide it. There's also a function that does this for us, but we can, sorry, I'm missing something. V. And we divide it by its variance, which is called F. As I told you, there is a function that does this for us. So later we will learn that function. But anyway, you can do it also by hand. Yeah, we have to turn this into a vector because this is actually a matrix inside, and this is an array of matrices inside. So actually, we should turn this. So just take that's just one element, but it's a matrix. So if we do this, we turn this into a vector, and again, this will work. No, it doesn't work as well. What's the problem here? Let me check. Oh, no, sorry. This is just a. Again, it's also a matrix. It should intuitively it shouldn't be a matrix, but it will. Maybe one day we'll explain you why. There's still something not going on. So that's why I should use the function to build this object. It's just because of the NAs, I think. Yeah, why there are NAs? Of course, I cannot compute the prediction error when I don't have data, right? So that's why I have some NAs here. And what about here? Oops. What's the problem here? Let's just check this. Yeah. Sorry, it's this way. Okay. Well, I just used the wrong dimension. It fades because there are NAs. We can just tell the ACF function to just skip the NAs. I don't remember how it works. NA function, yeah, NA action now is fail. We can set it to NA pass. Okay, still we have problems. Let's give it to some. So that probably we should use the function to extract that information. Sorry about that. No, it just doesn't work. Okay, then I present you the. I don't know why it's not working. Probably there are some zero infinite values here. Yeah, DNAs are there, but DNAs are really not a problem. Yeah, we have one infinite value. Why do we have an infinite value? Well, as I told you, the first prediction will be just terrible. So probably we have 0 divided by, it should be infinite, but probably it's if finite thing. So we get infinite. So that's the problem. So we should maybe just keep the first observations. Let's just keep the first year of observation. It would be more safe because
observation in F is 0, so we need one.
Yeah, because because I didn't show you there are actually two F functions, two X F. Sorry, KFS. There's an F, and an F infinite. Okay, so when it's infinite, it's not contained there, but it's contained here. The information. Okay. I don't even know how to read this. I never use it too much. But you see, probably, yeah, this is the part of the so-called diffuse Kalman filter. So that is managing the infinites at the beginning. So it's always a good policy to skip the first observations of the prediction error. And of course, for example, we can leave. Actually, a good choice would be let's leave so many observations out as the number of diffuse states. And we have 13 states, and they're all diffuse, so it would be a good policy to leave the first 13 observation out of the autocorrelation function. Now it works. Okay. Yeah, it's not bad. Yeah, we have just a couple of moments in which we have some autocorrelation that go outside of the bands, but basically it's not bad. Okay, check also the PACF. I mean, they're all small. Look at the numbers are very small. There are a couple of crossings, but it's really not a problem. So I would say from the memory point of view of the prediction errors, the model seems to be a decent one. Okay. So this is just a diagnostic check. What we can do if there are things that get outside here, well, we could add other components. I mean, ARMA models could be also components of such a model. So, but usually we tend not to use ARMA models inside here. But maybe an AR1 I could add it, but it doesn't seem to be that necessary. So for example, let's look at the component, okay? So for example, I'll just to be very like didascalic, I want you to see how to get them. So for example, the smoother, we can call it the like the smoother of the level, okay? And it's inside alpha hat, and we can call it by position or by name. If you check, it produces the same names we use, okay? So for example, this is the smoother of the level, and let's compare it with the filter of the level. The filter is inside ATT, if you remember. And of course, we can compare it also with the original time series, because the level in some ways is in the same unit of measurement of the time series. So we can produce the log of air passengers. Of course, this is, well, we can also back transform, but anyway, let's just check it with the log. So this is the time series we're modeling, and this is the whole time series, also with the last 2 years. And we can like draw the smoother, and we set it maybe to color, which is, I don't know, blue. Yeah, something very bad is happening there. I don't know. Actually, there were strange behaviors I had never seen. But anyway, this is terrible. I don't know what went wrong, and it's very bad for a first example that something so wrong happens. But I'm used to this kind of behaviors while you're in a lesson. And this is the filter. Apart from the fact that there is something really terrible happening, I have to check what's going wrong here. But so these are predictions. That's why I say it's really terrible, because the predictions are just like falling down, and there is no reasonable. I mean, there is no really reason for that, because the time series has been growing all the time. So there's something wrong going on. I have to understand what. It never happened in any lesson, this thing. But anyway, let's just for the moment. And I think also the seasonality was not caught fully, because if you see, for example, the blue line, it looks like it's shaking. It's kind of going towards the seasonal movement. So there's something wrong going there. Maybe I can change initial values. I don't know. We will try to fix that. But what I want you to notice is that the red line, which is the filter, is more, of course, noisy than the blue line, which is the smoother, because the filter, as I told you, they're both estimating the same object. They are estimating the linear trend, the local linear trend, sorry. Okay? But the red line is a like streaming data or real-time estimation of the trend. And the blue line is using all of the observation. Of course, this is the last observation we passed. For the last observation, the filter and the smoother are just the same object, because they're all based on data up to n. And of course, they fill up the missing observation in the same way. So they're perfectly the same thing. And again, look at how crazy the filter is at the first, I would say, 13 observation. That's because the filter just uses past and contemporaneous observations, and the initial values, as I told you, we're imposing infinite variance, telling that we know nothing about the level, the slope, and all the seasonal components at the beginning of the time series. And so at the beginning, it has to use this data to learn how these components are. And so the filter is just crazy at the beginning. So don't look at the filter at the very beginning, unless, of course, you can put initial values that are reasonable. In that case, probably also the filter is doing better. In this case, we said we know nothing about all initial components, set an infinite variance. Okay, filter begins being just crazy. The smoother is not crazy because it uses also the future information to estimate the initial values. And that's why it's doing a good job also at the beginning. Let's try to find out what's happening here to make things so stupid. I mean, it looks like everything was fine. So this is a monthly time series. This is fine. This is fine. I don't know. It looks like it could be just stupid initial values. I don't know why. Actually, let's put pretty big variances here. I really don't understand it. It's still estimating the same stupid things. This is just so wrong. Sorry, I have no idea why this is. I never saw such a bad thing. It looks like just the slope is moving. And of course, and all the rest is moving very slowly. Let's do one simple try. Sometimes, if numbers are too small, computers get crazy. So something I sometimes do is instead of working on the log of the time series, I multiply the log by 100. Let's see if that fixes something. And of course, the initial values have to be changed because now the variance of the y is much different. Oops, sorry. So you see now the variance is much larger, so we can, I don't know, set 100 here, 10 here, 10 here, 100 here. Let's see if it was a problem of initial values or, yeah, now it looks, it's incredible. I mean, were you getting the same estimate I did? So stupid?
Yeah.
Okay. So it's, this is even better. Okay, so the autocorrelation function now is better because it means the model works better. And what happened? I don't have to. Of course, I'm comparing the wrong time series. Sorry. Okay, now it's fine. It looked like a numerical problem. It's the first time that it happens to me, but it was easy to solve. So that could be a good option.
I just changed the variances instead of 0.1 and 0.001. I just changed it 0.01 and it's working. Maybe it was the wrong starting point.
So this doesn't witness on the stability of these models. But anyway, when they work, I mean, this is a very simple time series. So. Okay, now we can do the same comments we did before, but now we have more reasonable estimates. And this is, of course, the prediction just of the trend. If you remember, what's a local linear trend? It's a local linear trend, in meaning it's like we are always estimating a new line, a new straight line, based on new observations. In this case, what happens? Let's see. Let's comment on the values of the variances here. So what's happening now is this is usually what it happens when I estimate on this data. The slope actually has variance which is virtually zero. What does that mean? Well, the slope doesn't change over time, meaning that the trend we're actually fitting is just a random walk plus drift. Because if the slope doesn't change, then we have, as a special case, random walk plus drift. The seasonality is evolving, not so quickly, but it's evolving. And of course, we have some observation noise. for example, let's check the slope. Of course, we cannot check the slope in the same plot because the slope is not in the same, yeah, I would say unit of measurement some way. So we can just plot it alone. Well, let's create it. So this is the smoothed slope. And we can steal it from KFS1 $alpha hat. And then we extract the slope. I get, well, this is the smoothed one. We could also, of course, compute the filtered one. And let's just plot it. Okay, to you, it may seem something that is changing in time. But if you look at the left side of your plot, so the numbers, you notice that it's really not changing. Okay, it's just an optical illusion. Okay, it's changing by 0.00001. Okay, so the slope is fixed. Okay, it's some turn around, but it's nothing. So it's about 0.9, a little bit more. We're working in log times 100, so this is about almost 1% of increase every month, which, if you remember, if you go back to our first lessons, while we were using just regressions and so on, we already concluded that actually the rate of growth was almost 1%, circa 1% per month on these times here. So we kind of get the same answer. And this is really not moving. Okay, it looks like it's moving, but it moves so slowly that it just could be considered fixed. And of course, it gets fixed when we don't have observation, because this is actually a random walk with extremely small variance. But when we have to do the prediction of the random walk, we just have a straight line. Okay, we have a parallel, like a fixed number. Okay. What about the filter? Well, the filter will be moving a little bit more, of course, because it's the estimation of the slope based just on the past. Probably it goes outside of this range. Yeah, you see it. It's much more crazy. We should do a plot. And again, it's crazy at the beginning, but everything is crazy at the beginning in the filtering world. Also, one step at prediction world, just because we gave no information at the beginning. So probably if we skip the first 13 observations, we get something more reasonable. Yeah, okay, we lose the time series property, but anyway. Here we have some movements because, of course, the slope is locally estimated, but then it tends to go to about around 1%, okay? Okay, and of course, we can also plot the seasonal component. For example, the smoother, we can steal it from KFS1 $alpha hat. I think he calling, well, it would be the third object, but it's called Sdmtsa, something like that. I always forget the names of the seasonal component. Well, it's quicker just to. So Sdmtsa. So the first one is the component. All the other ones are just legs of that component. Okay, so let's just use the first one. You may check. You can also plot the other one and see they're just legs of this one. Of course, this is the smoother, so it will be good from the beginning. Sees. And of course, this is the seasonal component. It's much. Fix it anymore. Anyway, it's evolving. You see, it's evolving because, for example, these small peaks is changing over time, but it's evolving in a slow way, in a slow pace. Okay. And again, these last 2 years, you see they're identical. They're just prediction. Okay, the last 2 years are prediction. So we didn't have to do anything to build the predictions because we get it for free if we put missing observation. And of course, we can also get the signal. The signal was M, I think, called M. Now, these are like one step ahead prediction, the M equals M. And mu hat, yeah, it's a smoothed signal in some way. But all of them will produce prediction in the future. So the smoothed signal is just the original time series without the noise in some way, okay? But anyway, we can check that as well. So let's plot again our log of air passengers times 100. I can directly get the signal from here. It was called mu hat. Okay. Of course, the signal is almost coincidence with the real time series because there's just a little noise, some noise added to it. But then, of course, you see the prediction errors here at the end. So we're not doing a very great prediction. Okay. We're like underestimating. Let's try to do the same exercise, but now using the trigonometric seasonal component. So we will be writing our update function, okay? So I guess for the first time. So we can start with the second model. Kind of can do the same thing here, like copy. We can copy all of them and then just update. Well, I just copied this here. So we can call it, of course, model 2. And now, instead of dummy, we write trigonometry. We can just also write trig, whatever. Now, for example, let's look at the A1, which gives us all the state. So, of course, we have the level, the slope, and then we have all these trigonometric pairs. So you see, it uses also the star name, you know, seasonal trigonometric 1, seasonal trigonometric star 1, seasonal trigonometric 2, seasonal trigonometric star 2, and so on. And of course, it ends with just the 6, and the 6 star is missing. If you remember, when the number of season, in this case 12, is even, then you have to throw away the last sinusoid because it will be always 0, okay? And so again, we have 13 state variables because 2 are the level and the slope, and then we have 11, which are the trigonometric seasonal components. So the first pair is the slowest one, and the second pair is the second slowest, and so on. Actually, in this case, we could even choose, if we don't want to use all the sinusoids, just we could select. I don't want to do it here, but I want to show you that you can do this. This will be useful when we will be working on like daily data, for example. You can pick the harmonics. If I pick one, it means I'm just using the slowest one. So if I want just like the first three harmonics, so 2 pi divided by 12 times 1, 2 pi divided by 12 by 2, and 2 pi divided by 12 by times 3, I just send a vector that goes from 1 to 3, okay, for example. The largest number, of course, is 6, because it's 12 divided by 2, integer part, okay. So now we leave all the components in, but you can do that. And all the rest we leave the same. Yeah, we already done that. We cannot try to use the same initial values here, but we call this fit2, and we applied it to model 2. There's something that he doesn't like. Again, while you're doing lessons, the first time you get all these terrible results. For example, let's maybe steal the initial values from the last. So we can, for example, steal these ones. I like 8. Well, this is very small. I would leave something not so small. So I like inspire my initial values by the final value of the other model. Let's see if it's working. It's not working. What's happening here? I don't know what's going on. Sorry. As I told you, yeah, what I told you, we have to build the update function, which I didn't do, of course. So let's build the update function. Okay. There is a good reason why we get that error. Okay. So why do we need an update function? I show you why. Okay, we just have variances to estimate, but we have actually, in theory, many variances to estimate. Look at the Q of the model. It's huge, okay? It's a big matrix. Why is it so huge? Well, this is the eta, so the level disturbance. This is zeta, so the slope disturbance. But then all of these, which are 11, are disturbances of the sinusoidal components. And of course, there are many. And so if I want to use the update, the default update function, I have to provide just 13 initial values for these ones, and then we have also the age. So I have to provide 14 initial values. That's why it's sending an error. So, but we don't want to actually. This one is one variance, this one is another variance, but all the other ones are just one single common variance. And so that's why we have to have this information inside the update function. So I usually call the update function, well, this is the second model, so we can call it update 2. And how is the update function? Well, the help of the update function you get from the fit_SSM help. Here's described how the update function should be. So the update function has to start with a vector of parameters, which is called parse. Here there's an S. In the Optim there is no S here, there's an S, but anyway. And then the model. If you remember, what the function of this update function is, it takes the parameters from the vector, it puts the parameters in the right system matrices inside the model, and returns the updated model. Okay. So first of all, even before writing the update function, we have to decide like the ordering of the parameters in the parameter value. So we can already start with like the inits. Of course, there will be all variances, so we want them to be log. So we decide the order of the parameters. We can keep the order, for example, that also the update function uses. We also can give names. Why not? So this will be like the variance of eta. We can already start with an initial value. For example, here we want an 8. Okay, we set 8. Then there's the variance of the, I use this name, but if you like, I mean, you can also call it the variance of the level. Maybe it's more intuitive. It's not a variance of the level, it's the variance of the disturbance of the level, whatever you want to call it. I don't know if you like this or if you like the letter we used on the paper, whatever. Call it whatever you want. Then we have the variance of omega, so of all the sinusoids. Okay, again we start with 1. Why not? And that's just one variance, which is common to 11 different elements in the Q matrix. And then finally, we have the variance of epsilon, which we set to 2. Okay. So my suggestion is start by already building like the initial values. So you give yourself the ordering of the parameters. And here we have to give this two names. So this is something you always have to use, these names, parse and model. And again, we want to take the exponential of the parameters, so to produce the variances, because these are actually log variances, and assign in the right points. For example, from the model, we steal the Q. Remember one thing that I already told you many times, that actually these are all tridimensional arrays. In our case, they're all fixed in time, so they will have just like the last dimension is stupid. It's always 1. But in case they're time varying, of course they can be time varying. Okay, so for example, this will be the variance of eta, which is the first elements in the disturbance vector, and we take the exponential of the first parameter. Is that clear? You can even call it like, if you prefer, you can name it. We name them. We name them here, so you can name it here as well, whatever you prefer. Of course, if you want to use the name, you have to put names here, because then the obtain function will use the same naming as in the initial values vector. Okay. Then the second variance is the one of the slope disturbance, and so this would be the variance of the parameter theta. And then we have the same variance for the Q going from the third to the 13th element. So we can go with a diagonal trick. The strange things that R allows. So we're writing on the diagonal of this matrix, which is a selection of the Q matrix from number 3 to number 13. And they all get the same variance, which is the exponential of parse var omega. Okay. So yeah, this is the strange function that R has, but they're very readable. So actually, I enjoy them. But it's strange. We're writing on a function. It's not really happening, but it's just, as I showed you, it's just another function called diag arrow. So, okay. And finally, we have the h. Again, h, it's a scalar, but actually it's again a tridimensional array inside the model. And this is just the variance of epsilon. Okay? And we have to return model. Okay? As I told you, this is just taking the parameter vector elements and setting it in the right points of the state space form. Okay? So now we have to provide the model, which is model 2. The initial values we already have, we call them init. It's here. I'm not sure I ran this, so I run it again. And then we have to provide the update function, which I called upt2. Maybe I should I've called init2. Maybe I'll do it just for coherence of the whole thing. And now, hopefully, I will not get, sorry, comma is missing. What's the problem? I misspelled something, maybe. Where is it? So what's wrong here? Parse.
Maybe when we did Sdmtsa, it's Q222 instead of Q2.
Oh, sorry. Yeah. So this is the first lesson I'm doing 2 lives ago. I will, well, the next ones will even get more craziness. Okay, thank you. That was great. It worked, hopefully. So convergence was fine. We have some similarities. We still have the variance of this, which is large, and this one, which is very small, meaning that also this model finds a slope that is not changing over time. Of course, the seasonality is changing slowly, and there is some noise. So it's not very different from the other one, but probably this is somewhat larger. Anyway, let's try to, well, we didn't check if it provides a nice residual autocorrelation. So let's compute again the KFS function. We compute all the filters on all the smoothers. Again, we can, if we want to produce the ACF, well, I can show you the function to produce the standardized innovation, which I told you before. It's called R standard. R standard is actually a generic function in R. For example, you can use it in regression and will give you all the influence statistics and that kind of stuff. But if you apply it to a KFS model, for example, if you want to see the health, KFS object actually, what I'm missing? No. I don't know why I don't get the help. Yeah, there should be actually start. Okay. Ah, it's there. I don't know what I was, again, I did something wrong. Anyway, this is our standard you can apply after passing these filters and smoothers. You have a different type of residuals, which I'll tell you what they are later. As I told you, we have a way of finding out outliers and structural breaks by looking at the so-called disturbance smoother. We will see that later. And that is what this part is doing. But the default is so-called, it called them recursive residuals, but they're just the standardized residuals. So the standardized one step ahead prediction. So if you pass the KFS2 object, the default would be like the standardized innovation, which is here. Anyway, it's a time series, so you can compute the ACF. Probably there are some missing observation as well, yeah. So we have to change NA, what was that, NA action, plus, and it's working now. Okay, not bad. I mean, it's much better than the other one. It looks like we just changed. It's funny because we didn't change too much the model. We just switched from a stochastic dummy seasonality to a trigonometric seasonality. But I mean, the autocorrelogram is beautiful. I mean, everybody would want such a correlogram. Everything is inside the bands, even too good. And here as well. Okay, so it's extremely good. Let's see if it's doing good also on the prediction. Again, we can just compare the original time series. Actually, we can already like back transform all our prediction. For example, passengers, we can compare directly with air passengers. And so we can just keep the extraction of every component. For example, we can just look at the smoothed strand by using KFS2 alpha level. Okay. So last time I created new variables. Now we learn how that works. We can do it at once. And of course, this is in log, so let's take the expectation. Sorry, the exponential. Che problema c'è qui?
So the first
Cos'è?
it was multiplied by 10.
I didn't run that. No, what's the problem?
Era moltiplicato per 10
Ah, hai ragione, sì, quindi bisogna no, it was multiplied by 100, so I have to divide that by 100. And then take the exponential. But still, I have some problem here, which I don't understand. Alpha, So, what's going on? There's an error. I'm writing something stupid. So this is a good. So this closes that. This closes. I don't know. Why is this? Unused argument. So it looks like lines. Sorry. but I'm still in a wrong dimension. Sorry, I had to divide before the exponential. Okay, so this is it. Okay. Okay. In some way, it's smoother. This smoother is smoother than the other one, and it looks like it's catching maybe a little bit the increase here. But anyway, of course, you also can check the filter, but now we understood the filter, of course, is just like a noisy version of the smoother because it's a real-time estimate. So just to show it. And again, it's crazy at the beginning, but that's expected. It's something we already know. And of course, the prediction made by the smoother and the filter are just the same because they are based on the same information. So the prediction of the future. And the filter is just, as you see, it's some more sensible to the latest observation, while the red line is looking back and forth. So it's providing more stable prediction. Okay, I didn't build a confidence interval. We could do that maybe once as an exercise. After a while, we can do that. And then we can try to see how the prediction of this, the forecast of the original time series of these models are. So we can keep like the plot of the original time series. And as I told you, we can just produce the so-called signal, and the signal will be, of course, forecast in the future because there are missing observations for the last 2 years. So lines, we can extract from KFS2 the signal, which is mu hat. Of course, the transformation. Sorry about that. And yeah, they're still predicting, somewhat under predicting. Maybe they're a little better than the other ones. Okay. What about, for example, if we want to produce, well, we could produce confidence interval for the components because, of course, the components are unobservable. So we estimate them. So there's some uncertainty. And I told you we have the time series of the variances to build that. For example, just to build one example. Let's build the smoother and a confidence band for the smoothed level. So I don't know. Again, we can produce this one. We can produce that already for the final time series. So for the original time series. So you can take KF as 2 alpha hat. That would be the level. And we can, of course, then, well, we can divide this by 100 and take the exponential. Okay, so we built the central time series. And then for example, let's build the time series of the standard deviation of these errors, or the standard errors, or if you want to call it that way. How do we get that? Well, this is, of course, in the unit of measurement, log. I will not write that here because the name is too long, but it will be in the log metric. And this we can get from KFS to $V, this one V, the large one. It's a three-dimensional array. We want, so the level is the first. We could write level as well. I'm not sure if it's also the name in the variance covariance. We can check it. I don't know it. No, it doesn't have any name, you see. So we have to remember it's just in the first position. And this is like the time series of the variance of the first, of the smoother of this first component. If you want the standard deviation, of course, we want the square root. This is also nice to plot, just to check. Maybe let's make a line. Oops. So let's comment on this. Why do you think this is the shape of the Earth? Oh, we turn around, but that's not. Why is this the shape of the variant? So it starts larger, it goes down, then it goes to, I would say, a minimum in the middle of the time series. So around 60, I would say it's minimum. We could even check it. You know, there's which mean. Yeah, it's about around 60. Remember that we're just providing 120 observations. Okay, this last one are missing. So of course, you're the smoother, so you can look left and right and produce the best prediction you can. Of course, if you're in the middle of the time series, you have, I mean, the best view on that information, because you have a large set of information on the left and the right, so you provide the best predictions you can. So that's why the minimum is exactly at 60. And of course, the more you go toward the end or the beginning of the time series, the less old or new observation you have to make like a symmetric filter. And of course, you lose some predictability of the component. And then, of course, it ramps in the last 24 observation because there is no observation there. So of course your prediction are very uncertain about that. Okay, and so of course we can build, as I told you, like standard. Well, we can produce confidence intervals like. So we can feel like the lower and upper confidence interval. So we can take like, I would take this one. So we can actually take off here the, wait, so minus what? Minus we call that SMO2. So 2 times the standard deviation, 2 times is a confidence interval for 95% level. And then we divide everything by 100, and we take the exponential. Okay, and then we do the same thing with the upper bound of the confidence interval. So instead of a minus, we have a plus. That's it. I hope I did everything fine. So we have, well, we can always plot their passengers time series, and then we can plot. Yeah, we can also do fan plots, but I would have to remember how to produce them. So let's just produce a line plots. So this is the level, maybe red. And then we can also produce the bounds. So low, maybe you can go with the red color, but line type, I don't know, number 2. And we do the same thing with the upper. I didn't run it, maybe. Okay, so we have uncertainty everywhere because it's an unobserved component. We will never be sure about the real level. There doesn't really exist a level, so it's more like something abstract we're doing. But it's very important if you don't want to do, I don't know, you want to see if you're doing well or bad. The seasonality is just something that is bothering you. You're more interested into the trend to understand. In this case, if like the air passengers market is doing well or not. And the example here is like small inflection, small crisis. I think I put an example inside the e-learning on, or if I haven't, I can, on the effect of 9/11 and also on the war in Iraq, on the number of air passengers in Australia. So you see the impact of the, like, people were scared, so you have like an impact on a number of passengers, like the months just after 9/11 and in the period of the beginning of the Iraqi war in 2003. I have a couple of examples. If it's not there, I would put it there. Even though I'm using a component just to catch that, but it's interesting. So just to tell you that you can use these models not only for forecasting, but also to assess, for example, the impact of such events on a time series. But anyway, this was what I wanted to show you about the confidence bands. I know it's very, everything is very handcrafted, but of course you can use also the dashboard I'm working on that I show you. All these things are much more quicker to do using that dashboard. But anyway, I want you to understand what's under the hood. I think people that just is able to run software is very dangerous. So that's why I want to know exactly what's going on under the hood in these models. And then they were very powerful. You can use them in many different situations. So what else I promised you to see? Well, of course, we can do the same thing also for the signal. So the V of mu is the variance of the signal. So we have like prediction intervals for the real-time series. And well, we can do it once. For example, we can like repeat the same thing we did here for the signal. Let's just try to do this. I can just copy these things here, like, but we do it with the signal. And if you remember, the signal was called, I think, mu. I don't remember the structure of this. Yeah, it's just a long vector because we just have one time series. So at the end of the day, it's just like this. Okay. And the same we can do for the standard deviation. I think it was called V of mu or V mu, I don't remember. Let's just, yeah, V of mu. I guess this is also a three-dimensional array. I'm not sure. Let's just check it. Right. So we just extract this. And again, we can produce confidence interval in the same way we did here. Maybe there are also some functioning fast to doing all these things. I'm not sure, but as I told you, I'd like you to understand what's going on, where things are built, and so you have to pay a little bit of patience for that. So this would be well, this was kind of useless. It's called Sdmtsa signal. Well, this is easier to just substitute with this one. Okay, I think, yeah, I have it all. And now we can, again, I can steal it from here again, and we can adapt it for the signal. There's something wrong here. Sorry, the signal was already transformed. So actually what I have to do would be to multiply, because inside an exponential, the minus becomes a division. And anyway, if I want to reproduce exactly what we did before, let's just substitute. That's why I did that. I did it, but then I forgot why I did it. Now should be right. Yeah. Of course, the uncertainty about the prediction or the forecast, the future forecast, it's large. And indeed, the real observations are inside the bands. Okay. So the prediction is the continuous red line. The real are the black line. And of course, the interval include the real data. But of course, the bands are really large. Okay. Just trying to remember all the things I promised to show you. Okay, let's analyze a little bit the concept I expressed before of the so-called disturbance smoother, which is important, as I told you, for catching outliers, structural breaks, and so on. We just remind what the smoother and the filter is. But of course, we can pass filter and the smoother also on the residuals. So as I told you, we could get from, again, a newer version of the tools we use in, as I said, common filter goes back into the 60s. I think the article of Kalman was like in the late 60s. Then there's all this the stochastic evolution of the state space form, which goes more in the 70s and a little bit in the 80s. And then we have the smoother. I think the first smoothers are from the 80s. And the smoother at that time was computed differently. Then I would say in the 80s and 90s, there's 90s actually, there's a better algorithm for the smoothing. And these algorithms actually start from smoothing, as I told you, the residuals, and then building back the states. So we may call it like eta hat t given n. And this is like the prediction, the linear prediction, or the expectation, of course, if you assume Gaussianity, of eta being like the vector of disturbances, given all the data. Okay. And of course, we can also have the same thing for the observation noise. So we like project the observation noise. Oh, sorry. Obviously, given the model on the data. And of course, we can also get the, I don't know how to express this, maybe just like V. I think FAS uses V for all of these. So I'm not sure what letters, but I can call V of eta, which would be again, the variance covariance of predicting eta using eta t given n. No, maybe let's call this P for coherence with the rest. So P eta t given n and P eta P epsilon. Whoops. Wait, I want to be more coherent, as coherent as I can with CFAS. Wait. So you can express all what we write in paper using CFAS. What's KFS? Where's KFS? Here. Okay, so just to keep the same naming as here. Okay, eta hat and V eta. Okay, I'm using the right letters. I was using that, then I corrected them. So eta hat, V hat, Eps hat, V Eps. Okay, sorry about that. We just use the same symbol so we don't get confused. So let's go back to the V. Okay. So we have also like estimates of the errors or the innovation, the disturbance, whatever you want to call it. Well, innovation is something different. So disturbances or errors, whatever you want to call it, of both of the components and of the observation noise. And then we have this V is the error or the variance covariance matrix of the error you make while you're predicting eta using eta hat. But then there's another variance I'm interested in, which is the variance. So this would be the variance of eta hat about eta. But I would also need the variance of eta about 0, which is its mean, okay? And then we can call, I don't know how to call it, let's give another name. I don't know, I call it sigma, maybe. Sigma eta t. So this would be the variance of eta around its mean, which is 0, so it would be just. And the same thing we can do for epsilon. Okay, this is another object. They're of course related. I can compute RAM from the other one, but they are different objects. So the first one, we are really not that interested in. It's produced. We're not that interested because we're not trying to estimate the disturbance. We really don't care too much how well we're predicting the disturbance. But this is important because we can use it to standardize this and build what's called the so-called auxiliary residuals. So the auxiliary residuals practice, they're just like the etas. Let's take just one single eta divided by the square root of its variance. Okay. So if we're in the Gaussian world, this is approximately a normal 0, 1. And why is that important? Because if we get a very large shock, so for example, you see 3. In a certain point, this standardized, I don't know how to call it, maybe auxiliary residual eta IT. So if you see one of these auxiliary residual equal to 3, well, that's a large number for a normal distribution, okay? Let's analyze what that signals. Well, it depends on the components. So for example, if we take the trend or the level component, it means that there's a very large eta. What's a very large eta? Well, the meaning of a very large eta in this equation here, for example, if it's positive, is that we have like our random walk or local linear trend, and that suddenly jumps up and stays there, okay? So if I find there is a really large eta through the auxiliary residual, that means there is like a structural break into the trend, and the trend is just jumping up or down, of course, if it's negative. It's jumping down by a big pace, okay? And of course, you can do the same thing here. So this is the slope. If we find out that there's a very large zeta, probably we have like a trend that is increasing at this pace, and then suddenly it increases at a much quicker pace, okay? It changes the slope, or if it's negative, of course, it can go down. But of course, you can do the same thing also for the seasonality. If you see a large shock into the omega, it means probably the seasonality is suddenly changing. So looking at those auxiliary residual makes you find out if they're like structural break. And instead, if you look at the function of eta, of course, we have like, if you look at the function of epsilon, Well, a large value in epsilon is just an additive outlier. So if you find a large value here, it's just an additive outlier. Okay. And so this is like a diagnostics check we can do after fitting our model that helps you find those outlier and structural change like level shift, slope shift, even change of seasonality. But then what can we do? I mean, we find out there is such a change. How can I change my model so that it adapts to this change? I mean, these models are already adaptive, but probably if there is just a single point, the model will like react smoothly to that change. But I don't want a smooth reaction to that change. Maybe I want to allow an abrupt reaction to that change. So we can either act on the variances of all these components, but usually we don't do that. Like in a single large variance on one single time. But as I told you, that's one way to manage that, but we usually don't do that. Usually we build like regressors or features, however you want to call it. So for an additive outlier, of course, you just need to build a dummy variable. Like this is your dummy variable. It starts from 0, then it goes to 1 when there is the additive outlier, and it goes back to 0. So it's just a regressor that is always 0. Then there's the additive outlier. You leave 1. You can leave whatever number, but usually you leave 1. Then, of course, you put this as a regressor, and you solve the problem. And of course, for every single outlier that you may find, you get a new dummy variable. So one dummy variable for every outlier. What about the level shift? So the level shift. Well, the level shift is just a change of the level. So we can use something called like a step function. So dummy variable would be E1 when t is equal to the date, let's call it tau of the event, and 0 otherwise. Okay. The step function instead is 0, and then it changes to 1 and stays there. So it would be equal to 0 for t smaller than tau, where tau is the event date, and 1 is for t starting from tau. Okay. Then I have to let you notice one thing for the timing. What about this is maybe more complex, maybe you come up with some idea for a slope shift. How would you build a regressor for the slope shift? Any idea? I mean, the other two were kind of intuitive. What, a multiplier? No, we can only put like additive regressors. So we're in a linear model. So, well, it's usually it's called a ramp. A ramp is just something that starts from 0. So this is 0. And then from the event on, it just starts counting the time. And of course, that will impact just the slope. So it's more like 0 for t smaller than tau, and then will be like t minus tau plus 1 starting from tau. It's just like counting. But I have to let you notice one thing. Let's look at the state space form. Look at the timing. If I find out on the auxiliary residual of the epsilon an extreme point, then you see that the effect is immediate. So a large epsilon means a large y, okay? Immediately. This doesn't happen on the second equation. A large eta means a large alpha, but next time, so t plus 1. So recall that when you find an extreme observation on the disturbance, like what we call eta, all the etas, then the dummy variable or the step variable or the ramp variable has to start from the next time. So you have always to add 1. Okay. So I'm not sure there is such a thing on the air passengers, but we can check it. There are, of course, time series that have more crazy movements. Of course, we are in time of a lot of things happening, like the COVID, like wars. And so all of these sudden changes are much more showing up in the recent time on economic time series, social time series, and so on. And so that's actually a nice tool to have. But let's just for now apply it to the last model. So for example, let's add to the last filtering. Well, maybe let's just do a new chapter. We can rewrite the KFS2 by adding one more. So we had the KFS2 somewhere here. I copied. We have to add the disturbance smoother. Okay. So this disturbance smoother, now we check it, produces exactly the prediction, so the linear prediction or the expectation in case of Gaussian models of the etas and also the epsilons on the data. And indeed, you can now find, for example, KFS $2 or eta hat. Now there's a eta hat, for example, just, or we can view it. Okay, why do we have 13 columns? Well, because in this model, this is the model with the trigonometric seasonality. We have one disturbance for every equation. I didn't show you how to build the seasonal component here. We have to make that as well. Maybe let's make the seasonal component before doing this, because now the seasonal component it's simple. The seasonal component is not a single component inside the state vector, but we have to sum up all the cosine in the state vector. So let's before going to the auxiliary residual, I'll show you how to build the, for example, the smoothed seasonal here. Of course, we can select them from KFS to from the alpha hat. We have to select all the non-star component of the seasonal state variables. So let's look at the column names, okay? So these are the name of the component, and you see it's called C-trig1, and then there's C-trig*1. Remember that we have just to pick up all the C-trig but not the C-trig star, okay? We can either use numbers, maybe it's a simpler thing, or use like something like grepl or those functions that work on the strings. Actually, we want all these components, but not these ones. Maybe you can use like formal expressions, but I think it's much more work than just using the numbers. We just use number from 3 to 13 every second observation. So it would be a sequence starting from 3 to 13 up to summing every time just 2. So we're getting on this one, we're getting this one, we're getting this one, and so on. Is that clear? And then, of course, we have to sum all the sinusoids. I mean, if you look at those, I mean, this would be many of them. Just let's plot them so you can understand what I mean. This is all the sinusoids composing the seasonal component, okay? So this is the seasonal component decomposed into its sinusoids. And there's 6, of course. This is the slowest, the smoothest, and this is the quickest. And you see they evolve. Actually, this one evolves not that much, but the little ones, they're evolving much quicker. But if you look at the range, actually, the low frequency ones are much more important. This is moving between minus 15 and 10 or 15. And this is just moving between minus 1 and 1. So this is much more, explaining much more of the variance of the seasonality. But then I have to sum them up, okay? So in order to sum them up, for example, we can do the row sums. There's a function for that. And we sum, of course, this by time. And so this is the, whoops. Well, it's not more a time series. Now it's just a vector. And this is the seasonal component. So when we use the trigonometric version, we have to build the final component by, there is no single seasonal component in the state vector. We have to sum up all the sinusoids. And you see we get something which is not far away from what we saw from the other one. Okay. It looks like it's adapting more quickly than the other one. That is, we could compare them, but for example, I could add the other one, lines. It was, I think I overwritten over that, but okay, so I don't have it anymore. Doesn't matter. They will probably similar, but it looks like this moves a little bit quicker. Anyway, this was something I forgot you to show. So before moving to the auxiliary residual, I wanted you to check this. And of course, for example, when we'll be working on high frequency data like daily, hourly data, whatever, we will be using just low frequency sinusoids to adapt the very long seasonalities of this time series. So like maybe 6 sinusoids would be enough for even a hourly time series, okay? For the within year seasonality. Of course, for the 24-hour seasonality and for the 7-day seasonality, we will probably needing more than you sinusoid. But anyway, this is just to show you how it works. You see, it's just the stochastic, these are just stochastic sinusoids. It's very similar to what we did at the beginning of this course using deterministic sinusoid. The only difference is these are evolving over time, okay? And the other one just stay equal. Of course, if we put the variance of this seasonal component to 0, we would get exactly what we saw when we do that into a regression problem, okay? Okay, let's go back to the auxiliary residual. So I just added this disturbance smoother here, and I showed you that we have so many. In this case, we have 13 noise elements in the noise vector. Then we also have, of course, the epsilon. And so, for example, if I want to check a level in the shift, I'm interested in the shift in the first. No, this V1 would be eta, this V2 would be zeta, and these are all the omegas. But these are not standardized. And actually, we also have a V hat, it's here, V hat, but this V hat, or whatever you want to call it, is this one here, which is not the one we are interested in. We want to standardize eta and epsilon. And in order to standardize, I need these sigmas, not this V. Because these V are the errors I make for estimating eta using eta hat. But in order to standardize eta, and so that I can compare it with a normal distribution, with a standard normal distribution, I want to divide by the variance of eta, which is not what we get automatically from the KFS function, okay? In order to get the auxiliary residual, which is just the standardized version of eta hat and epsilon hat, we have to use that function called R standard, okay? So it's like residual standardized. That's just the name they picked up. So, for example, the auxiliary residuals for the level, well, let's call the auxiliary residual for the state disturbance. That we can get by applying that function, R standard. We have to pass a KFS2 and specify we want the state related auxiliary residuals, okay? And now if you look at the names here, maybe we can view the whole thing. Now, actually, it also builds names. You see it. It's nicer. It gives this is like the auxiliary residual of this residual relative to the level equation and so on. And it builds also, of course, here we have many seasonal because we have many shocks driving all the sinusoids. And these are already standardized, so I can compare them with a standard normal distribution. So, for example, where if I do the plot, I get too many. I think we cannot plot so many things. Yeah, of course, more than 10 time series is not allowed. Let's go with the first two, maybe. What's this? As I told you, this is an estimation of the residuals or disturbance of the level and of the slope. As I told you, this time series is very regular. It kind of all stays between -2 and 2. You see it from here. See, so it's from a like extreme value. If you compare with the Gaussian distribution, we don't see really many extreme values here. In fact, this was a regular time series, and there is really no change here going on. Yeah, there are some maybe here. This is maybe a little bit extreme. We like an exercise. We could pick this one as the most extreme and try to put like a level shift here. Now this is like a downward level shift. Okay. It's about -3. Okay, -3 is a large number for a Gaussian distribution. Maybe we have also a couple here. So on the positive side, I don't see any extreme movement. With the slope, we saw the slope actually almost doesn't change, so it's kind of, yeah, it's not moving that much. You may notice that, okay, these are like estimate of a white noise process. So this is a white noise. What we are estimating is a white noise process here and here. Of course, this is not a white noise process. it cannot be a white noise. Is that strange that the best estimate of a white noise process is not a white noise process? Not strange, because we are using the same data. So we are projecting those white noise on the same vector of data. And so, of course, all those estimates will be correlated. So it's not strange. It's the right way. It's the only way it can be, okay? This looks a little bit more white, but this is really not white. Okay, so just as for the sake of the example, we can now check also if there are like outliers, additive outliers. Or for example, we could also see if there are like changes in the seasonalities. That would be stranger. Of course, that starts from the 3rd and it goes to the 13th. It's exactly no, it's 11. Well, just check the first 12. You see, also, even the disturbance here are estimated to be sigmoidal. But sometimes there are some, for example, here there's like an extreme observations. It's more complex to treat the change in the seasonality. We may reason about that, but yeah, here there's like extreme. There's a moment where it looks like there is some kind of jump also in the seasonality around this date. But anyway, this was more for curiosity. I didn't even give you a solution to the change in seasonality problem. So let's check also the disturbance for the observation noise. So this would be our auxiliary residual for like the observation noise. And for some reason, which I didn't understand, I don't understand, the name here is Pearson. I don't know why it's called Pearson, but I mean, this is a Finnish guy that made this package. I have to ask him why he chose Pearson. But here's just one time series, of course, because we have just one y variable, so we have one noise. And here, okay, we see a couple of outliers. Here, there's an outlier. If we take 3 as a reference, for example, of course, 3 is arbitrary, but it's a large number. For a normal distribution, it's very extremely rare to observe something outside 3, I mean, for a standard normal. So maybe this could be an additive outlier. Well, maybe these ones as well. But for the sake of an example, maybe let's just take this one. Let's just take one single extreme observation from this one and one single observation from the level disturbances, and just build a dummy variable and a step variable. Okay, so for the level shift. So level shift index, we can call it this way. We can use which is max and take the absolute value of the our auxiliary residual of the state disturbance of the level. Here we also have the name, so we can use the name. So I'm just taking the most extreme observation of the auxiliary residual, extreme in positive or in negative, because I'm taking the absolute number, the absolute value. Okay, and this index is equal to, well, so it's observation number 53. But remember that this is happening on the eta at time 53, but will affect the time series one time later, so on time 54, okay? Maybe we can even see it by eyes, I don't know, by visual inspection, maybe not. We can do an AB line. We put the vertical on, this time it's LS index plus 1, because we will see that with a delay on the time series. Okay, it's not working. Why? Because this is a time series, so it's using the date. We can do this. Sorry about that. We can take the time of, for example, air passengers and use it. Great. So what's not working here? Invalid. I don't know. Because maybe it keeps it as a time, as a TS object. That just doesn't like it. Higher quality, sorry. I'm using the wrong time series as well. Here, air passengers. I didn't even know there was an air quality time series. Good. So actually, we don't notice it. Why we don't notice it? Well, just because the seasonality is kind of hiding things. But actually, you notice that something here is different from here somewhere. But I mean, by visual inspection, we would have never noticed there was a level shift here. Okay. Okay, that it means that it's useful what we do using the auxiliary residuals, because some visual inspection of some other algorithm that in some way follows our visual inspection rationality probably wouldn't find that. Okay. Okay, so let's see also, just to do just one more model instead of two of them. So let's build one for the observation error. So again, we can, in this case, it would be an additive outlier index. We do the same thing, which max with the absolute value of the, we call the auxiliary residual of the observation error, noise, actually. And this is usually more visible, so we can plot this. I didn't do it here, but anyway. We can draw both of them, like AB line, AB line. So one vertical line, we put at LS and X. Sorry, the time of. This is what we already seen, and this is the new one. Oh, this is LS index plus one, and this is not plus one because this is contemporaneous. Okay. Maybe this was more visible, maybe not. Even this one is not that visible. Also because, I mean, here the dominating feature is the seasonality, and that kind of hidden muscle of the things. So to finish the example and letting you go, let's create a dummy. A good strategy here is, since this is a time series object, just copy the air passenger and then overwrite the numbers. So this is a time series with the same dating. And then we just fix dummy at, we call that our index equal to 1. Okay. So this is a time series of zeros and one. And if you're good, you can find the one. See it. Maybe they didn't pass it. Here. Okay. So this is the dummy variable, and we can build the step function, the step variable using the same rationality. We set everything to zero, and then starting with the level shift and the x plus 1, I think, well, here we can use the length of the time series, and we set this to 1, right? And this is the step time series. Now we can steal our last model, which is here. Well, let's steal everything here. Well, actually, we can exploit the same update. We will see the update function doesn't change. The initial values, they don't change. Well, I copy everything and I just delete the update function, or just repeat it. It doesn't really matter. Maybe we can call everything number 3, so model 3. How do we add the regressors? Well, we add them here, like maybe the step, the dummy. And let's see how the regressors are managed within the system. You see it from here. This function, SS model, always put the regressors coefficient. Remember that if you put a regression in state space form, the state vector contains the regression coefficient that are constant over time. Okay, so these first two will be just the coefficient of the step regressor, the coefficient of the dummy variable, and of course the zeta matrix will be time varying. You see it from here, and we have the regressors inside it. So you see that it contains the step variable, the dummy variable, and then all the unobserved component. Now it's a tridimensional array with many observation on the third dimensions as the length of the time series, okay? But our update function doesn't have to change, or we can keep the same initial values, because we didn't add any new noise, okay? We're just writing the variance of the noises, of the various noises, the various disturbances, okay? And we're not adding any new disturbance because the coefficients are just constant, so they're just identities, okay? And so we can exploit everything without changing nothing. Well, we estimated the model. Of course, now we should add the effect of the change in the level inside the level component. So, for example, I would call the smooth. Oh, we have to pass the smoother. We pass so the fit free model. Well, let's just compute the state smoother. So just to be quick. And the smoothed level, now I would say it should contain what? Well, surely it contains the smoothed level, okay? So this is the smoothed level. But now I would add to the level also the change, the sudden change due to that jump, okay? That is, of course, the coefficient, which is actually a constant. I'll show you it's constant because so this is just, you see, it's just the coefficient of the step function. It's constant because it doesn't change over time, okay? So we just add that, and here's the step multiplied by, well, we could use the step function itself, okay? So we add, actually it's a downward change. So okay, let's just plot log air passengers times 100 and the new level. And then we're done. Okay. Now here, somewhere here, there's a jump, sudden jump here probably. So it was going up and then it went this way. I don't know if the prediction got better. We could check that. I will finish this example with all the rest. But this is just to show you how we changed the level. We found like a level shift in the level, and we fixed it into the model. Okay. Just to show you all these things you can manage in just one place using these models. You don't have to, missing values, outliers. You can like manage all those features here. Good. If there's no question, I would stop here.